Great. So our next talk is a continuing in the series of metaprogramming. This one's going to dive a little bit deeper than some of the previous ones did, and hopefully it's not too technical. I haven't actually looked at this one since last week sometime. I don't remember the contents that well. So take it away, Ben.
Okay. You can all hear me, right? Okay. Well, I've got a talk here. It's compile time abstraction techniques for the D programming language. Okay. My name is Benjamin Shropshire. I'm a Christian. I am a student at the University of Idaho. I am a mechanical engineering major, computer science minor. I work as a computer developer and as a student researching computer security. Covered the who I am, now on to the why, what, when, and how. Okay. First of all, what? What is abstraction? Particularly, we're going to be talking about compile time abstraction. I'm just going to refer to it as abstraction to save a little time. Abstraction is a device for removing unnecessary complexity, for concealing it, for hiding it. We use abstraction to distill intent, so we can say what we want to happen rather than how it happens. We also use it to reduce redundancy in some other ways. Just a sec here. I guess I'm not going to see all my notes. Why do we use abstraction? The primary reason we use abstraction is to save time. We save the programmer time when they write the program. We save them time when they maintain the program, and sometimes we can even save the user time by making the programs faster. We save time when we write the program by being able to isolate complexity. We don't need to deal with as much of the program at any given time. We can look at a small piece of it and, for the most part, ignore the complexity around it. We save time when we maintain it by having a separation of concerns. So you have the implementation and what it's implementing, and if one of those is wrong, you can fix it, and the other one can remain unchanged, and everything just sort of falls out. Why do we use... when to use abstraction, excuse me. When to use it. Use it for things that it's good at. Use abstraction where the computer is very good at doing things. This is tasks that are monotonous, very well defined, and fairly detail critical. Also, keep an eye out for where it really works, like the canonical swap function. It just sort of works, and that's a good place to do it. When to not use abstraction. Did you get the previous slide? That one? Okay. When to not use abstraction. Well, when it doesn't work. If you find yourself trying to force what you're doing into the abstraction that you're using, then you're probably wasting your time. It's sort of the no silver bullets thing, is nothing works everywhere. And when it doesn't work, well, it causes problems. Okay, now into the how. I've got several examples here. I've got nested templates for various reasons. I've got what I've called chain recursion, which is a new technique which I've ran into while trying to do something, and nested tuples, which can get some very interesting results. Plus, I've got a use case down at the end. Okay, nested templates. One of the major issues with tuples is dealing with multiple lists, multiple sets. Tuples can concatenate automatically, so you've got issues when you're trying to separate them out again. How do you find the boundaries? How do you know what it is? Well, one easy way to solve this is just nest your templates. Each template has its own one, and you end up with you have the first tuple there, you have the second tuple there, and then you can use them inside. Pretty simple example. Another advantage of this is it lets you actually name things in a way that is useful. Is that font big enough? Okay. For instance, you got this template here. Remove the first, third, and fifth element from this tuple here. Well, zero-based indexing, so remove that guy, that guy, that guy, giving you that there. Quite readable. sort of goes into the domain-specific language kind of thing, where you try to make the syntax read well and describe what you're interested in. Another example, chained recursion. Now this one is kind of funky. Uses aliases. What you've got is a mix-in template here that mixes in a variety of actions. You start out with one template, you mix it in there, and you instance this template. I use a set manipulation example here. Start out with the range from start to stop. Then you mix in this example here, and it generates aliases to things in this template here, which, interestingly enough, mix in exactly the same template, which gets you back to, well, right where you started. So you end up with this infinite recursion here in templates. So you can just keep instancing them along. For instance, here's the example here. There's the original instance. Add on this other range here. Add on another range. Drop this range here. And you end up with this set here. Quite clean. And you can add as many of those things as you want. And, well, OK, you actually run into compiler limits fairly quickly, but it looks cool. Nested tuples. We did nested templates, now nested tuples. One of the templates, for some reason, don't like having tuple aliases inside of them that aren't the only element and named the same as the template. So you can't have multiple tuples in there or whatnot. However, you can stick them in structs. So you can have a struct with several aliased tuples inside of it. And then you can do, so this is a specific example, is pretty useless actually, but it illustrates the point, is you end up with, you alias the template, and then you can use it and for each over it and generate various pieces of code from this. Another important point is the struct here is handy because it's a lot easier to iterate using the static for each over types rather than mixed tuples, which comes up later. Well, I guess I covered that stuff already. I got ahead of myself. OK, now, a couple of use cases for this. Compile time parsing and compile time parser generation. First one, compile time parsing. Compile time parsing consists of two parts. First, you read the data, and then you build the tree from it. So do these together in a template. Here's a template for an instance for parsing that rule there. It attempts to parse the first bit of both of these. If it succeeds, it attempts to parse the second part, and either way, it builds some aliases underneath of this that let you access the data later. This one actually generates a tuple of Ds. So this rule is basically a sequence of Ds. Works quite well. Another one, a little bit more complicated, a B followed by a CA, again a recursive rule. It'll generate a list of Bs separated by Cs. And works about the same, a little bit more complicated. It's, if you stare at it for a little bit, it's not that hard to understand. By the way, the code examples from here will be available online later. And the way you'd use it would be like this. You'd have a instance the template A with a string in there, and it gives you a template with a list of with a couple of tuples in there, and then you can iterate over them using some static for eaches, and you can walk through the tree. Now, where would this be useful? Well, I've written a template parser generator, and its input is a grammar string. So I need to be able to parse the grammar before I can implement it. So you parse the grammar, then you select the production instance, and then you generate the function to do it. I chose a recursive descent because it's fairly easy to implement. You just walk through it. You try each disjunct, and you just walk through that, trying the things, backing up as necessary. Actually, the implementation is very similar to what you do for a runtime evaluation of a dynamically defined grammar. There's really nothing spectacular in it except for the parsing, which I just showed you, and there's nothing really spectacular there either. So, I mean, which actually I think is a good thing, is it's quite interesting, quite useful, and actually quite boring in the innovation standpoint. Well, in my innovation, Walter there has done all the innovation I need. This is the pseudocode version of it. You parse the grammar there at the top. Then you have a rule. Pick the rule you want. Iterate through all the disjuncts. Iterate through the little parts, recursing to other rules. And when you're done, you do the action and return. Very simple. And it appears I actually went faster than I thought I would. Does anybody have any questions?
Well, I just have a statement. It seems this is very interesting for L systems, for the recursive nature of like turtle graphics as well, where they're driven by these patterns, like one of the things you had on there. I don't know if you've seen like artificial trees where they can.
Yeah, fractals, L systems. Yeah, I've run into those.
Yeah,
Never used them, but.
It's an interesting approach to creating a parser for actually parsing those alphabetic strings.
Mm-hmm. Yeah. Yes?
So it seems to me that you could create something like a regex parser with this.
I would assume you could actually generate a compile time regex evaluator. I didn't even bother, but you definitely could make a regex evaluator if you can. Actually, no. Mostly I've done proof of concept grammars. I've got a few grammars that are designed to test corner cases, but nothing particularly elaborate. Yes? Which one? Oh, yes, that one. Yeah. Yes, it's the mix-in. Originally, I wrote it completely expanded. The mix-in template is actually just to clean it up a bit. What you have here is this guy aliases this template here instanced with some parameters for this guy here. And so does this template here also instances or aliases itself with some parameters for the outer template. So the outer template carries your state, and the inner template, you pick an inner template, and it does a little bit of manipulation and then aliases back to itself. It took me a while to wrap my head around it when I wrote it. And is that enough explanation, or would you're interested in some more? Yeah, I do. Well, if anybody's.
This terminates because you only evaluate as far as you actually tested the extension, right?
Yes, it's.
It's driven by the string that you gave it up top. I mean, it doesn't go on forever. It actually terminates when it ends at the end on its input.
Yes, yeah, what it amounts to is that the template evaluation is lazy. It's a good thing, too, because this wouldn't work otherwise, saying you'd probably end in a segfault or a Stack Overflow.
Just as clarification, I mean, I've tried doing recursive mixes before. What usually happens is that the last part of your recursion works. Every other, instance beforehand just gets thrown away because tuples get evaluated differently.
I'm not following. I'm interested, but.
Well, when you
Mm-hmm.
Usually what happens is that you have to plug in different batteries in your last scope, so that your previous, if you modify the people and call it a different one, it gets discarded.
Yeah, I'm afraid I probably haven't exactly run into that. I do know that there's some issues with mix-ins from different scope don't overload nicely, which causes some issues when you use the parser generator I've got, because it uses overloading to do the actions and the terminals.
Does it slow down the compiler very much?
Actually, this one doesn't seem to slow it down very much. Mostly it seems to cause segfolds. I think I hit stack limits well before I hit processing limits. I mean, that's one thing I'm sort of hoping we'll get later, is a compiler that's better able to handle these kinds of things. Yes?
Go back to your grammar example,
That one?
So I noticed that you were giving it a string, but how does it pick off the individual characters in the string?
What it does is, the basic premise here is you look at the front of the string and check to see if it's the first thing you're interested in. And if it is, you take that off, and then anything that's left over, you alias or make a static constant for the rest of it as remainder. And then each template can look at the remainder of the string and pick off its front. So you just say, okay, I want a DB. So okay, ask the D template to parse off a D. Well, okay, it does whatever it needs to, and then when it comes back, you have an alias to a template, and you can say, okay, what is the remainder after that? And then I need to parse off a B off of that, so then I ask B to parse off whatever it needs to. And it just, each thing just keeps chunking off the front of it and leaving the rest behind for whoever called him to use.
I still don't see how you're getting the first character and computing the remainder.
Oh, yeah. I left that out. Is the D template here, when you instance it, it checks the front. It's the terminal. It checks the front, sees if it's correct. If it is, then it comes back with D.match being true, and a remainder in there that you can use then for the next part. LL. Probably probably LL without any clean closure or plus operators or star operators or any of those. You could probably do question mark fairly easily, but I don't think you'd want to try anything particularly complicated. But it's reasonably powerful, but not spectacularly so.
Great. Well, we'll take another short break.